At precisely 1 minute past midnight on November 8, 1942, the inaugural keel plate for a new Liberty ship was carefully positioned at Kaiser Permanente Metals shipyard, specifically at Yard No. 2 in Richmond, California. A mere 4 days, 15 hours, and 29 minutes later, the completed hull gracefully slid down the launching ways into the waters of San Francisco Bay. This vessel was christened the SS Robert E. Peary. Remarkably, just 1 week after its keel was laid, it was fully outfitted and delivered to the merchant marine. By November 2, the SS Robert E. Peary departed Richmond, bound for active combat duty. This ship marked the 47th Liberty vessel constructed at that particular yard, boasting a build time that was a mere fraction of the industry standard. Its construction largely relied on welding rather than riveting, utilizing prefabricated steel sections manufactured at inland facilities and transported by rail. The media dubbed this achievement a signature stunt, while Henry Kaiser himself referred to it as an incentive ship. German engineers, poring over wire reports filed in Hamburg, Bremen, and Danzig, regarded it as something profoundly different, a methodology they would be compelled to emulate. 2.5 years later, on the evening of April 30, 1945, the very afternoon Adolf Hitler ended his life in a Berlin bunker, a German submarine quietly departed its moorings in Bergen, Norway. This was the U-2511, a Type 21 U-boat, representing the pinnacle of submarine design at the time. Germany had commissioned 119 such vessels, yet the U-2511 was the solitary one to ever undertake an operational war patrol. For days subsequently, with the war drawing to a close, it returned to Bergen without discharging a single torpedo. The remaining 118 Type 21s remained moored at their docks, utterly unseaworthy. The hull sections, which German shipyards had attempted to replicate from Kaiser's innovative method, failed to fit together during final assembly. The welding flaws were catastrophic, rendering the boats unfit for deployment. This narrative explores the profound reasons why an American engine, fabricated in Detroit, could be uncrated on a Normandy battlefield in the summer of 1944 and installed into any Sherman tank within approximately 4 hours. Conversely, it illustrates why German mechanics, attempting the same feat with their domestically produced Panther tanks, spent countless hours hand-fitting components that should have been interchangeable. Ultimately, the war was not decided by a superior tank, but by superior part interchangeability. You are watching WW2 Tales. To comprehend the astonishment of German mechanics in 1944, we must journey back almost 150 years. In 1798, Eli Whitney, an inventor from Connecticut, secured a contract with the United States War Department to supply 10,000 muskets. He pledged that the components of these firearms would be interchangeable, meaning a lock from one musket would seamlessly fit into any other without requiring filing or manual adjustment. In January 1801, Whitney conducted a renowned demonstration before President John Adams and Vice President Thomas Jefferson. He meticulously arranged the parts of 10 muskets on a table, then had Jefferson assemble a functional firearm using randomly selected pieces. It worked flawlessly. However, this demonstration was, in fact, a deception. Historian Merritt Roe Smith, in his seminal work Harper's Ferry Armory and the New Technology, proved that Whitney had pre-selected and hand-fitted these parts in his Connecticut workshop, labeling them specifically for the demonstration. Smith concluded that Whitney deliberately misled government officials. The true industrial breakthrough occurred elsewhere and unfolded gradually, primarily at the federal armories in Springfield, Massachusetts, and Harper's Ferry, Virginia. At Harper's Ferry, a gunsmith named John H. Hall, operating under contract to the War Department, dedicated 2 decades to perfecting manufacturing techniques that yielded parts with such precise tolerances that they were genuinely interchangeable. David Hounshell, in his book, From the American System to Mass Production, identifies Hall's 1819 breech-loading rifle as the first product ever made in large numbers, whose components could be freely exchanged and still function. This achievement took 20 years of relentless effort, involving the development of jigs and fixtures, bespoke milling machines, and hardened steel gauges that allowed an inspector to assess a finished part in a single second. It also entailed 2 decades of rejecting non-conforming parts and discontinuing relationships with suppliers who delivered too many faulty components. By the time the British hosted their Grand Crystal Palace exhibition in London in 1851, American gunmakers astonished attendees with revolvers from Samuel Colt of Hartford and rifles from Robbins and Lawrence of Windsor, Vermont. The British were profoundly impressed, coining the phrase, the American system of manufacturers, to describe what they witnessed. Britain subsequently formed a committee, dispatched it across the Atlantic to Springfield in 1850, and placed orders for American machine tools to re-equip its own Royal Small Arms Factory at Enfield. The technology that originated in Connecticut and matured in West Virginia then traversed back to Europe, yet Europe never fully embraced it. European industry, and German industry in particular, clung to its traditional culture, maintaining what Germans called the Fabricated, the skilled craftsman, at the core of every workshop. A component produced on a German lathe in 1905 was meticulously finished by a craftsman using a micrometer and a file, taking immense pride in achieving a perfect fit. In contrast, the American part was deemed complete by a gauge. When the Second World War commenced, this fundamental difference would ultimately determine the outcome. In May 1940, German tanks swept into France, leading to the French army's surrender within 6 weeks and the British evacuation from Dunkirk. President Franklin Roosevelt, seated in the Oval Office, posed a critical question: who in this country could actually build the weapons America was going to need? The financier Bernard Baruch provided the answer in 3 concise words: first, Bill Knudsen; second, Bill Knudsen; third, Bill Knudsen. William Knudsen, a Danish immigrant, arrived in New York Harbor in 1900 at the age of 20. He ascended through the ranks of the Ford Motor Company under Henry Ford himself, orchestrating the assembly lines at Highland Park that produced the iconic Model T. He later transitioned to General Motors, becoming its president by 1930. Knudsen possessed an unparalleled understanding of industrial production. Roosevelt offered him the monumental task of overseeing American war production, which Knudsen accepted, relinquishing a salary exceeding $300,000 annually as president of General Motors for a federal salary of $1. Knudsen adhered to a core manufacturing principle, which he frequently articulated: speed produces nothing in manufacturing. Accuracy is the only straight line to greater production. In the plants he managed, he was renowned for confiscating hammers and files. If a part failed to meet the gauge's specifications, it was immediately discarded. It was not adjusted, tapped, or filed to fit, it was rejected, and the supplier was put on notice. Beginning in 1940, Knudsen rigorously enforced this principle in every contract, every plant, and with every supplier in the United States seeking to produce weaponry. He urgently required tanks. In 1940, the United States Army possessed fewer than 400 tanks, almost all of them obsolete. Knudsen sought someone capable of mass-producing modern medium tanks. He approached K.T. Keller, the president of Chrysler, who agreed to the undertaking. Knudsen then enlisted Albert Kahn, the architect responsible for designing the Ford Rouge complex and the Highland Park plant. Kahn drafted plans for a tank factory on 113 acres of farmland in Warren Township, Michigan, just outside Detroit. Ground was broken in September 1940, and the first M3 Lee tank rolled off the assembly line on April 24, 1941, even before the roof of the facility was completed. This colossal facility, dubbed the Detroit Tank Arsenal, stretched 5 city blocks long and 2 city blocks wide, housing 1,000 machine tools and 8,000 specialized jigs. In December 1942 alone, it produced 907 Sherman tanks. By the war's end, Chrysler had manufactured an astonishing 25,059 tanks at this single site and had returned approximately $50 million to the United States Treasury due to coming in under budget. Across the nation, 10 other factories joined Chrysler in building Shermans. The Fisher Tank Arsenal in Grand Blanc, Michigan, operated by General Motors, produced 11,358. Pressed Steel Car in Illinois built 8,147. Pullman Standard in Pennsylvania manufactured 3,426. American Locomotive in Schenectady, New York, Ford Motor Company at Highland Park, Lima Locomotive Works in Ohio, Baldwin Locomotive in Philadelphia, Pacific Car and Foundry in Bellevue, Washington, Federal Machine and Welder in Warren, Ohio, and Montreal Locomotive Works in Canada contributed to this monumental effort. These 11 plants, collectively, produced nearly 50,000 Sherman medium tanks by the war's conclusion. The precise figure, according to R.P. Honeycutt's authoritative reference, the book simply titled Sherman, is 49,234. Herein lay the crucial difference: a tank assembled at the Detroit Tank Arsenal in Warren, Michigan, and one built at Pacific Car and Foundry in Bellevue, Washington, 3,000 miles away on the opposite side of the continent, utilized perfectly interchangeable parts. Bolt patterns aligned, mounting brackets fit, shaft splines matched, and the transmission could be unbolted and removed as a single unit. The engine bay accommodated any of 4 entirely distinct power plants, designed and built by 4 completely different manufacturers. Within the Sherman family, 4 engines from 4 companies all fit the same hull, a feat unprecedented in industrial history. The first engine was the Continental R9, a 9-cylinder air-cooled radial that originated in 1928 as an aircraft engine, the Wright J6 Whirlwind. It generated 400 horsepower at 2,400 revolutions per minute. Continental Motors produced over 53,000 of these for armored vehicles at its East Jefferson Avenue plant in Detroit and its Muskegon, Michigan, plant, roughly 7 times the number Wright had ever built for airplanes. The Sherman installation incorporated a power-driven cooling fan and shroud to compensate for the airflow typically provided by an aircraft propeller. This engine was installed in the M4 and M4A1 Sherman variants. The second engine was the General Motors 6046 twin diesel. This comprised a pair of Detroit Diesel 6-71 inline 6-cylinder 2-stroke diesel engines linked to a common output shaft, each retaining its own crankshaft so that either could operate independently if the other failed. Total displacement was 850 cubic inches, yielding 410 gross horsepower, with a total weight just over 5,000 pounds. This engine powered the M4A2 Sherman, of which almost 11,000 were constructed. The Marine Corps favored these due to diesel fuel's reduced flammability compared to gasoline when a tank sustained a hit. The Red Army received nearly 5,000 of these through Lend-Lease. A Soviet after-action report from the 5th Guards Tank Brigade, dated October 23, 1943, stated that, compared to the T-34, the M4A2 was easier to control and more durable during long marches because its engines required infrequent adjustments. The report concluded that the tanks performed admirably in combat. The third engine, more than any other, exemplified the extraordinary capabilities of American industry, the Chrysler A57 Multibank. In 1942, the Army's demand for tank engines surpassed the combined production capacities of Continental and General Motors. Chrysler was tasked with rapidly designing a new engine. With no time to develop a power plant from scratch, 2 Chrysler engineers, Harry Wolff and Richard Hicks Wilson, alongside Mel Carpentier, ingeniously took 5 ordinary 250.6 cubic inch inline 6-cylinder L-head engines directly from the Plymouth assembly line and clustered them around a central crankcase. These 5 engines drove a single common output shaft through helical gears. Total displacement was 1,253 cubic inches, with a total of 30 cylinders, 5 carburetors, 5 distributors, and 1 water pump, producing 425 horsepower. 5 car engines bolted to a single shaft. The most astonishing aspect was its flawless operation. The A57 Multibank proved to be the most reliable tank engine within the entire Sherman family. Data from Aberdeen Proving Ground in 1944 indicated that crews operating the Multibank Sherman spent only 45 hours on engine maintenance during the test period. Figures for other engines were significantly higher: 110 hours for the M4A3 with the Ford engine, 132 for the M4A1 with the Continental, and 143 for the M4A2 with the twin diesel. British crews utilizing the Multibank reported an average distance of 4,000 kilometers between major overhauls. Chrysler produced 9,965 of these engines between April 1942 and September 1943. Almost all were supplied to the British, who used the Multibank Sherman as the foundation for the Sherman Firefly, the sole Allied tank in the Western Theater equipped with a gun powerful enough to reliably penetrate the frontal armor of a German Tiger or Panther. The fourth engine was the Ford GAA V8, and its origin story is one of the war's most unusual engineering serendipities. In 1940, Ford had been developing a V-12 aircraft engine, hoping to secure a contract with the United States Army Air Corps. The contract never materialized, as the Air Corps was committed to the Allison V-1710. Consequently, Ford possessed a fully designed, all-aluminum V-12 with dual overhead camshafts and a 60-degree bank angle, with no immediate application. The Army Ordnance Department inquired if it could be adapted into a tank engine. Ford's engineers removed 4 cylinders from the castings, retaining the 60-degree bank, the all-aluminum block, the dual overhead camshafts, and the gear-driven accessories. The result was the Ford GAA, an 18-liter, all-aluminum V8 with dual overhead camshafts, generating 500 gross horsepower at 2,600 revolutions per minute, an engineering specification akin to a modern Formula One engine. Ford was manufacturing this engine at its Lincoln plant in Detroit in 1942 for installation in tanks destined for deployment in mud and snow. Approximately 28,000 were produced, powering the M4A3 Sherman, including the E8, the jumbo assault tank, and ultimately the M26 Pershing heavy tank. For entirely distinct engines, from 3 engine companies and 1 tank manufacturer that built them, were supplied to 11 assembly plants. Regardless of which engine was utilized or which Sherman variant it was bolted into, it fit perfectly. The bell housing matched the transmission input shaft. The mounting brackets corresponded with the engine bay rails. The cooling shrouds bolted on seamlessly. The bolt patterns aligned precisely. Hoses connected without issue, and wiring harnesses plugged in effortlessly. The parts simply dropped into place. In the orchards and sunken farm lanes of Normandy during the summer of 1944, the United States Army applied this principle in the field. The outcome, documented in an Armored Force Reliability Study cited in Honeycutt's Sherman, came directly from an anonymous American tanker. He stated that changing an engine was a straightforward task, taking little more than 4 hours, and that it beat all hollow the best time achieved by the Germans. How did one army accomplish this feat when the other could not? The solution lay in the meticulously organized maintenance framework the United States had established even before the global conflict began. Army maintenance operations were structured into 5 distinct levels. The first level involved the tank crews themselves, responsible for routine daily checks and lubrication. The second level saw unit mechanics performing minor field repairs. The third echelon consisted of divisional ordnance companies, carrying out medium-level repairs in mobile workshops often set up discreetly under natural cover. The fourth echelon comprised heavy maintenance battalions operating at the field army level, undertaking comprehensive tasks like full engine and transmission replacements, hull welding, and main gun exchanges. The fifth and final echelon was dedicated to depot rebuilds, conducted at facilities in England, Italy, or even as far back as arsenals within the United States. In the European theater, this entire system reported to Major General Henry B. Saylor, who served as the Chief Ordnance Officer for the European Theater of Operations. Saylor, in turn, reported to the Chief of Ordnance in Washington, Major General Levin Hicks Campbell. Jr. Campbell had assumed leadership of the entire Ordnance Department in June of 1942. His very first general order upon taking office explicitly stated that any member of the Ordnance Department, regardless of their rank, encountering bureaucratic obstacles in their duties, was to disregard such red tape. Campbell concluded this directive with the emphatic words, "Accept that, please," as a definite general order. Under Campbell's leadership, the Ordnance Department transformed into an industrial powerhouse, managing a budget of $30 billion annually. The production cost of TNT plummeted from 55 cents per pound during the First World War to a mere 6 cents per pound by the end of the Second. Similarly, the price of a Thompson submachine gun dropped significantly, from $200 in 1941 to just $21 by 1944. These impressive figures were not achieved by simply demanding more effort from workers, but rather through the relentless implementation of standardized parts produced in massive quantities. In Normandy, Campbell's innovative system faced its inaugural trial by fire. The 526th Ordnance Heavy Maintenance Company spearheaded this critical test, landing on Dog Green Beach at Omaha on June 9, 1944. A portion of the company had been lost when LST-1006 was struck in the channel 2 days earlier. The detachment that successfully made it ashore was under the command of Captain Francis F. Poppenberg. Within 48 hours of reaching the beach, his men were already engaged in repairing battle-damaged Shermans. Poppenberg later received the Bronze Star, with a citation commending his heroic task in refitting, repairing and keeping in operation badly needed tanks. Other ordnance units advanced swiftly, following closely behind the combat divisions. The 2nd Medium Maintenance Company, the oldest ordnance company in the United States Army, with a storied lineage tracing back to Chateau Thierry and the Meuse Argonne in 1918, established the first forward ordnance shop near Magdeburg by June 13. The unit's historical records note that they labored long into the night, using flashlights inside blackout tents. The 3rd Armored Division's Maintenance Battalion arrived on July 4, bringing ashore their own M25 Dragon wagon tank transporters, 12-ton tractors built by Pacific Car and Foundry capable of towing a disabled Sherman from the front lines back to a rear collection point. At these collection points, ordnance crews meticulously evaluated each damaged tank. If the hull was deemed reparable, replacement parts were retrieved from crates, and the tank was swiftly returned to service. If the hull was beyond repair, all salvageable components were stripped out for use on other tanks, and the remaining hulk was crushed. These maintenance battalions often improvised on the fly when circumstances demanded it. In the 3rd week of July 1944, an American cavalry sergeant named Curtis G. Coolin Jr., attached to the 102nd Cavalry Reconnaissance Squadron, devised a steel hedgerow cutter. He fashioned it from welded German anti-tank tetrahedrons that the Wehrmacht had left scattered across the Normandy beaches. This cutter consisted of 4 sharpened steel prongs welded to the front of a Sherman, designed to slice through the dense earthen banks the Germans were utilizing as defensive positions. The 25th Ordnance Heavy Shot Battalion, under Brigadier General John B. Meteris, constructed nearly 300 of these cutters in just 48 hours and welded them onto 3 out of every 5 First Army Shermans within a single week. They accomplished this feat just in time for Operation Cobra, the pivotal breakout that finally ended the Normandy stalemate on July 25. 300 custom-built field modifications, designed by a sergeant and mass-produced by a heavy shot battalion in 48 hours within a combat zone, records from Ordnance Battalion histories, such as Beachhead and Battlefront, by Leader Mayo for the United States Army Center of Military History, document dozens of similar operations. These included engine swaps, transmission replacements, gun barrel exchanges, and hull patching. The American maintenance system was not merely keeping the Army operational, it functioned as a second factory operating directly in the field, sustained by an Atlantic supply line that consistently delivered identical, perfectly fitting parts. By the autumn of 1942, the German Army faced a significant challenge. They had been contending with the Soviet T-34 medium tank since June of 1941. The T-34 boasted thicker armor, a more powerful gun, and wider tracks than any German tank then in service. The Panzer III was undeniably outclassed, and the Panzer IV was, at best, its equal. Hitler consequently ordered the development of a new medium tank that would decisively outperform the T-34. 2 companies vied for the design contract. Maschinenfabrik Augsburg-Nürnberg, known as MAN, submitted one design, while Daimler-Benz, at its Berlin-Marienfeld plant, submitted another. Hitler personally favored the Daimler-Benz design due to its resemblance to the T-34. However, the Heereswaffenamt, the German Army Ordnance Office, ultimately selected the MAN design on July 11, 1942, because the new Rheinmetall turret, with its long 75mm gun, would only fit on the MAN hull. Thus, the Panther had been chosen. But a critical issue soon emerged. MAN alone could not produce the Panther in the quantities the Wehrmacht desired. The ambitious plan called for 600 Panthers per month by January 1943. Consequently, the Heereswaffenamt licensed the design to 3 other manufacturing plants. Daimler-Benz, the firm that had initially lost the competition, was instructed to retool and build Panthers based on MAN's blueprints. Maschinenfabrik Niedersachsen-Hanover, abbreviated MNH, commenced Panther production in mid-1943. Henschel and Sohn at Kassel constructed Panther chassis, with turrets supplied by the adjacent Wegmann firm, which were then assembled on the Henschel line. Multiple plants were thus licensed to build the same tank. On paper, this seemed a logical approach. After all, the Sherman was produced at 11 different facilities. However, the Speer Ministry had failed to grasp the subsequent complication. The Heereswaffenamt assigned every Panther component a unique drawing number, known as the Gruppenummer. The historian Thomas L. Jentz, whose book, Germany's Panther Tank, co-authored with Hilary L. Doyle, stands as the definitive technical study of the vehicle, elucidates the reason for this. Jentz explains that the Gruppenummer identified the precise component parts belonging to each of the various Ausführungen, or versions, of the Panther. The core of the engineering disaster resides within that very sentence. The reason each part possessed its own drawing number was that the same nominal part, for instance, a Panther Ausführung drive sprocket, was, in reality, several distinct physical parts depending on which plant had manufactured it and at what stage of production. A Panther Ausführung drive sprocket built at MAN in October 1943 was not dimensionally identical to a Panther Ausführung drive sprocket built at Daimler-Benz in October 1943. They might have looked similar and performed the same function, but a recovery yard mechanic could not simply remove one part and bolt on the other. The chassis number had to be meticulously checked, the drawing number verified, and the part often had to be hand-fitted if it would fit at all. Jentz and Doyle meticulously document specific variations across every Panther subassembly. Drive sprockets differed between plants. The commander's cupola transitioned from a welded drum type to a cast type at one chassis number at MAN, at a different chassis number at M&H, and yet another distinct chassis number at Daimler-Benz. The Schürzen, the thin steel skirts designed to detonate hollow-charged shells before they reached the main armor, utilized different mounting brackets at MAN compared to M&H. The engine deck exhaust shrouds varied. The turret rotation drives varied. The hull machine gun ball mounts varied. In a 2011 interview, Thomas Jentz summarized his findings from the German archives. MAN did not care what a Tiger tank looked like. The assembly workers would assemble a vehicle with whatever was on hand and whatever was most easily accessible. He was not even referring to the Panther in that particular quote, but rather a different German tank built by the same firm. This principle permeated the entirety of German armored vehicle production. The Facharbeiter, the skilled craftsman, was central to every assembly hall. He had his calipers, he had his file. If a part didn't quite fit, he made it fit. He was a professional. He was proud. In a sense, he was the best in the world at what he did. And he was the reason an American Ordnance Battalion in Normandy could swap a Sherman engine in 4 hours, while a German panzer division recovering a Panther in the Ardennes could not. The Panther was undeniably beautiful and lethal. Its 7.5 cm KWK-42 gun was the most accurate tank gun of the war. The frontal armor, 80 mm thick on the glacis plate angled at 55 degrees, was effectively impenetrable to almost every Allied tank gun in service in 1943. A Panther could destroy a Sherman at 2,000 yards, while a Sherman firing at a Panther's front plate could rarely penetrate at any range. But for the gun to fire, the Panther had to be running, and the Panther was rarely running. The engine powering the Panther was the Maybach HL230P30, a 23-liter, 60-degree V12, water-cooled gasoline engine with a cast iron block and cylinder heads, nominally producing 700 metric horsepower at 3,000 revolutions per minute. The engine alone weighed 1,200 kilograms, or about 2,600 pounds. It was built at Maybach Motorenbau in Friedrichshafen, and after April 1944, also at the Auto Union plant at Chemnitz. The HL230 had been designed in haste. It was an enlargement of the earlier HL210, which had powered the first Panthers and the Tiger I. Engineers had increased the bore of the smaller engine to gain displacement, but they had maintained the original cylinder spacing. This meant that the metal webs between adjacent combustion chambers were dangerously thin. Head gaskets repeatedly burned through, not at the perimeter where failure would typically be expected, but between the cylinders themselves. The result was catastrophic engine damage. That was not the only problem. The fuel lines in the engine bay leaked, and the carburetors frequently overflowed, drenching the engine compartment with raw gasoline. A spark from the magneto or a hot exhaust manifold could instantly turn the engine bay into a fireball. Panthers often caught fire during their approach marches, before they had even fired a single shot in combat. Soviet engineers at Kubinka, who examined captured Panthers in 1943 and 1944, documented failure modes including burnt head gaskets, burst connecting rod bearings, broken connecting rods, cracked cylinder sleeves, and water in the exhaust manifolds. The engineers at Maybach continually attempted improvements. In September 1943, they added copper sealing rings to the cylinder head grooves, a fix personally suggested by Ferdinand Porsche. They also reinforced the fuel pump diaphragm spring. In November 1943, the factory locked the engine governor to 2,500 revolutions per minute instead of 3,000, which reduced the rated power from 700 horsepower to about 600 and decreased the Panther's top road speed from 52 km per hour to approximately 45. A British interrogation of a captured Panther crewman in June 1944 revealed that his battalion was averaging only 450 miles between engine failures. Yet, this was not even the most critical flaw. The worst problem was the final drive. The final drive was the gearbox that transferred engine power, after the transmission, to the drive sprocket on each side of the tank. The Panther's final drive employed a simple spur gear system. Thomas Jentz, in Germany's Panther Tank, on page 147, wrote that the final drive was the weakest part of the Panther. He continued, it was a risky proposition to use a spur gear system for transferring the drive power, especially considering that the available steel during the war did not have a particularly high stress tolerance. The root cause of this failure was something Albert Speer himself admitted he was unaware of in his post-war memoir, Inside the Third Reich. The Panther had originally been designed as a 30-ton tank. However, Hitler continuously ordered more armor and larger guns to be added during the design process. Speer wrote that, in the course of a year Hitler once again insisted on clapping so much armor on it, as well as larger guns, that it ultimately reached 48 tons, the original weight of the Tiger. The final drive had been engineered for a 30-ton tank. It was now being asked to transmit power through that same single spur gear to a 48-ton tank. Jentz documented that in March 1944, 13 final drives were replaced in 30 Panthers in one unit, a 43% replacement rate in a single month of normal operation. After the war, French Army engineers evaluated captured Panthers at the Army testing facility at Vincennes. Their report concluded that, the truly weak spot of the Panther was its final drive, which was of too weak a design and had an average life of only 150 kilometers, just over 90 miles. That was the distance a Panther could be expected to drive before the gears in the final drive sheared. Furthermore, the steel that should have been used to properly harden those gears was running out. The Watertown Arsenal Metallurgical Examination of Enemy Ordnance, published in February 1945, documented the steady decline of German armor steel quality. Before the end of 1943, German armor sections contained 0.3% to 0.55% molybdenum, a crucial alloying element that imparts toughness to steel. By 1944, the same plates contained only 0.15% to 0.25%. The most recently examined sections, the report stated, contained no molybdenum at all. The German alloy supply was collapsing. The massive Nikopol manganese mines in Ukraine fell to the Red Army in February 1944. The Norwegian Naben mine became Germany's sole source of molybdenum. The Petsamo nickel mines in northern Finland were lost in September 1944 when Finland signed an armistice with the Soviet Union. The Balkans, with their chromium, were lost that same autumn. Portuguese and Spanish tungsten shipments dried up in mid-1944 under Allied diplomatic pressure. By 1945, Panther front plates, supposedly the most invulnerable armor of any tank in the world, were spalling. When a Soviet 122mm shell struck a late-war Panther glacis and failed to penetrate, the plate itself often cracked from the impact, and large fragments broke off the back of the armor inside the crew compartment, killing the men who were supposed to be protected. These were the deteriorating conditions under which Germany was attempting to build the most sophisticated tank of the Second World War. The Panther was scheduled to make its combat debut at one of the largest battles in human history. The summer of 1943 saw the German offensive, Operation Citadel, targeting the Soviet salient at Kursk in central Russia. 200 Panther tanks were assigned to Panzer Regiment 39, known as Regiment von Lochert, named after its commander, Major Meinrad von Lochert. This regiment was part of Panzer Brigade 10, an elite unit within the Grossdeutschland Division, itself belonging to the 48th Panzer Corps of the 4th Panzer Army. General Heinz Guderian, the Inspector General of the Panzer Troops, had spent weeks attempting to dissuade Hitler from this offensive. Guderian was convinced the Panther was not yet ready for battle and that the entire German armored force would be squandered for no gain. During a meeting in Munich on May 3, 1943, Guderian directly challenged Hitler, asking, "Do you believe, my Führer, that anyone even knows where Kursk is?" Hitler's response was that he was gladly wrong, adding, the thought of this attack makes my stomach queasy. Despite these misgivings, the assault proceeded 2 months behind schedule, launching on July 5, 1943. Even before reaching their assembly areas, many Panthers began to fail, with several catching fire during the road march from the railhead. On the morning of the attack, only 184 of the 200 issued Panthers were operational. Within hours of the initial push, 18 Panthers were lost on the first day at Sokaskoye. By July 7, an additional 6 had burned out due to engine fires during the approach march. By the evening of July 6, only about 40 remained operational. Guderian conducted an inspection visit to Regiment von Lochert on July 10. His report, preserved in the Bundelkirch archive at Freiburg under file RH10/64, detailed his findings. By the evening of July 10, he wrote, there were only 10 operational Panthers in the front line. 25 Panthers had been lost as total write-offs, 23 were hit and burnt, and 2 had caught fire during the approach march. 100 Panthers were in need of repair. 56 were damaged by hits and mines and 44 by mechanical breakdown. 60% of the mechanical breakdowns could be easily repaired and were on the way to the front. About 25 still had not been recovered by the repair service. Out of 184 operational Panthers at the jump-off, only 10 were still in the line 5 days later. By the end of July, the regiment's overall operational rate had stabilized at a mere 16%. A captured after-action report from Panzer Regiment 39, dated July 11, concisely summarized the engineering catastrophe. Until reaching the first preparation area, the report stated, 50% of the vehicles were inoperative, 2/3 of them with engine breakdowns, and 1/3 with the lateral transmission system. Despite these widespread failures, the Panther's formidable gun was so lethal that even a quarter of the regiment inflicted significant damage. The 48th Panzer Corps reported destroying 559 enemy tanks by July 15, with Panthers claiming 269 of these kills. However, this marked the zenith. Operation Citadel was personally cancelled by Hitler on July 13, and the Red Army immediately launched its own counteroffensive. Guderian later concluded about the campaign, by the failure of Citadel we had suffered a decisive defeat. From now on the enemy was in undisputed possession of the initiative. The Panther never fully overcame its mechanical reliability issues. Right up to the war's conclusion, Panther final drives consistently failed at a fatigue life of 150 kilometers. A reinforced final drive was not introduced until September 1944, more than a year after the problem became known to German engineers. Redesigning and retooling would have halted Panther production for months. Instead, Panthers rolled out of the factories of MAN, Daimler-Benz, M&H, and Henschel with a known fatal flaw from their first day of service until Allied infantry marched through those very gates. By May 1943, the Kriegsmarine, the German Navy, faced its own crisis. 41 U-boats had been lost in a single month during Atlantic convoy battles, effectively ending the U-boat war. Admiral Karl Donitz, who had been commander-in-chief of the Kriegsmarine for only a few months, presented Hitler with a proposal. Germany would construct a new generation of technologically advanced U-boats to revive the Atlantic campaign. The proposal was approved on May 31. Naval armaments production was transferred from the Kriegsmarine's own construction office to Albert Speer's Armaments Ministry. The new design, designated Type 21, featured a streamlined hull derived from earlier high-speed submarine experiments. It boasted 6 times the battery capacity of any preceding U-boat, granting it unmatched underwater endurance and speed that no Allied destroyer could rival. It could remain submerged for days and outrun a corvette underwater. Had Germany been able to build them in sufficient numbers, it might have restored the balance in the Battle of the Atlantic. Speer hired Otto Merker to oversee Type 21 production. Merker, a truck builder and general director of the Magirus Werke firm in Ulm, which manufactured fire engines and army trucks, had no experience building submarines or any kind of ship. He was specifically chosen as a manufacturing expert, not a naval architect, as it was believed that applying truck plant assembly methods would enable mass production of U-boats. Merker decided that the Type 21 would be built unlike any U-boat before it. Rather than being constructed keel-up in a slipway, the vessel would be divided into 8 prefabricated hull sections. Each section would be built at a separate inland steel factory, with roughly 32 different subcontractor steel firms producing sections simultaneously. The completed sections would then be transported by rail and barge to 3 final assembly yards, Blohm and Voss in Hamburg, AG Weser in Bremen, and Schichow in Danzig, where they would be welded together. Mercer pledged to Speer that the first boat would be delivered in April 1944, with production escalating to 30 boats per month by autumn. Friedrich Schwerer, the actual chief naval architect at the construction office, objected. He advocated building a single prototype first to resolve design flaws before initiating series production. Schwerer's request was overruled by Mercer on grounds of maintaining the schedule. No prototype was ever built. The Type 21 proceeded directly from the drafting room at the Ingenieurbüro Gluckhoff in Blankenberg into series production at 32 factories previously in use for submarine construction. The ensuing disaster was almost inevitable. Historian Marcus O. Jones, writing in the Naval War College Review in 2014, summarized the events. The tolerances involved in submarine construction were and remain extremely exacting, Jones wrote. Type 21 hull sections were initially delivered to the shipyards with deviations of up to 3 centimeters in some instances, necessitating their dismantling and proper reconstruction with immense expenditure of time and effort. Pressure testing revealed potentially lethal defects in the welding of the initial boats, a consequence of poorly fitting components, new inspection standards, and construction methods unfamiliar to the facilities performing them. 3 centimeters, more than an inch of deviation, on a pressure hull designed to withstand the immense weight of 200 meters of seawater, was catastrophic. The 32 inland steel firms, accustomed to building structural steel for buildings and bridges, had never welded a submarine and lacked the appropriate inspection equipment. Pressure tests at Hamburg, Bremen, and Danzig repeatedly exposed welding flaws. The Kriegsmarine's manganese-saving order of April 1944, which altered the formula of the high-strength ST-52 steel used for U-boat hulls, rendered the welds even more brittle. Hulls cracked under test, forcing sections to be cut apart and rebuilt at the assembly yards, precisely the delays Mercer's modular system was supposed to eliminate. Clay Blair, in his 2-volume history Hitler's U-boat war, plainly described the outcome. The hastily prefabricated boats, made in 32 factories, resulted in 8 major hull sections that were crudely made and did not fit together properly. The reason for the poor fit was the absence of a central tolerance authority among the inland steel firms. There was no William Knudsen at Speer's ministry inspecting factories and rejecting faulty parts. Each subcontractor independently determined what was good enough. Of the 119 Type 21 U-boats commissioned by the war's end, almost none were operationally ready. The United States Navy's official War Damage Report No. 58, citing the Naval Technical Mission in Europe's Technical Report 312-45 from August 1945, recorded that while the boats were delivered by the final assembly yards, none became operational due to high-pressure hydraulic system defects. The diesel engines were fitted with superchargers that malfunctioned, causing the designed horsepower of 2,000 to drop to an actual 1,200. The designed surface speed of 18 knots plummeted to an actual 15.6, making the Type 21 slower on the surface than a Royal Navy convoy escort. The hydraulic system, which controlled diving planes, rudders, and torpedo tube doors, was situated outside the pressure hull, exposed to seawater corrosion and, critically, inaccessible for repair from inside the boat. Only one Type 21 ever undertook an operational war patrol, U-2511, commanded by Korvettenkapitän Adalbert Schnee. She departed Bergen, Norway, on the evening of April 30, 1945, the afternoon Hitler shot himself in his bunker. On May 4, Schnee received Donit's ceasefire order. According to Schnee's later account, he had achieved an attacking position on a British cruiser at 500 meters, dived deep, and returned to Bergen on May 5, without firing a torpedo. A second Type 21, U-3008, under Kapitänleutnant Helmut Mansek, sailed from Wilhelmshaven on May 3, 1945. She received the ceasefire signal while submerged near a convoy, made no attack, and surrendered at sea on May 11. That comprised the entire operational career of the Type 21 program: 2 patrols, 0 torpedoes fired. A senior German naval engineer estimated after the war that each Type 21 consumed armaments-grade steel equivalent to 30 German army tanks. Marcus Jones, in his Naval War College Review article, concluded that the program cost the German war effort some 5,000 tanks, 5,000 Panthers, 5,000 Panzer IVs, at a time when German army formations on both fronts had been reduced to skeleton strength. This is what happened when Germany attempted to replicate American mass production. The Reich possessed no Springfield Armory, no Hall at Harper's Ferry, no legacy of the gauge tradition. It tried to leap directly to mass production without ever having mastered standardized parts, and this leap proved fatal. By the spring of 1945, with the Reich in its final weeks, German army repair depots across Western Europe were overflowing with broken Panthers awaiting parts that would never arrive. The German Panzer Commission's reliability census in January of that year counted 500 defective Panzer IV final drives, 370 defective Panther final drives, and 100 Tiger failures, all waiting for replacement assemblies. The replacements never materialized. The factories that built them had been bombed or overrun or were producing at a fraction of capacity because steel and alloys had run out. Across the front, Allied ordnance battalions were doing precisely what Campbell's General Order in 1942 had instructed them to do, throwing red tape out the window, putting tanks back into the fight. When the war in Europe ended on May 8, 1945, the United States had produced 49,234 Sherman tanks, almost 90,000 armored fighting vehicles of all types, more than 30,000 heavy bombers, 2,710 Liberty ships, and over 150 aircraft carriers of all classes. The country had transformed itself in 5 years from a depression-scarred economy into the greatest industrial military complex in human history. After the war, William Knudsen was asked how it had been achieved. His answer became one of the most candid summations any production man has offered. "We won," he said, "because we smothered the enemy in an avalanche of production, the like of which he had never seen nor dreamed possible." He was correct about the avalanche. But the deeper truth was that the avalanche had been built on a foundation laid down 140 years earlier: Springfield and Harper's Ferry, John Hall's breech-loading rifle of 1819, the American system of manufacturers showcased at the Crystal Palace, Henry Ford's moving assembly line at Highland Park, Knudsen confiscating hammers and files, K.T. Keller at Chrysler, Albert Kahn designing the Detroit tank arsenal, Campbell throwing red tape out the window, Medeiros building 300 horsepower tank. Hedgerow cutters in 48 hours. That was the system. That was the inheritance. When a Wehrmacht mechanic in a captured ordnance depot in 1944 cracked open the engine deck of a knocked-out American Sherman, lifted out the destroyed engine, and was handed a fresh one straight from a wooden Detroit crate, he saw something his entire industrial culture had never produced. He saw a part that did not need him. He did not need his caliper. He did not need his file. He did not need to spend 3 hours dressing the bell housing flange to make the new engine seat against the transmission. He just had to bolt it down. It dropped right in. The Panther, on paper, was the best tank of the Second World War. The Type 21, on paper, was the best submarine. Both were brilliant designs produced by brilliant engineers in a country that had given the world Daimler and Benz, Krupp and Zeiss, Bosch and Maybach. None of it mattered. What mattered, in the end, was whether the part dropped in or had to be hand-fitted. America had been answering that question for almost 150 years. Germany had never answered it at all.